This episode of Engineering the Future is brought to you by Manulife, OSPI's life and health insurance partner. Thousands of engineering professionals trust the protection of Engineers Canada-sponsored insurance plans. With affordable association rates and flexible plan options, we think there could be a plan that's right for you and your family. To learn more about these exclusive life and health insurance plans, visit manulife.ca/OSPI.
This podcast is brought to you by OSPI, the Ontario Society of Professional Engineers, the advocacy body for professional engineers in the engineering community in Ontario.
Welcome to Engineering the Future, brought to you by the Ontario Society of Professional Engineers. I am your host, Jerome James. In today's episode, things start to get heated and cooled as we explore the vital role engineers play in advancing eco-friendly heating and cooling systems to combat climate change. We'll explore sustainability in homes, the benefits of retrofitting, and key design considerations for efficient HVAC systems. And joining us today to help navigate this hot topic is Yannick Trottier, a professional engineer with a degree in aerospace engineering from MIT. Yannick specializes in building decarbonization. He is also a committed climate change advocate. Yannick, welcome to Engineering the Future. And joining us today to help navigate this topic is Yannick Trottier, a professional engineer with a degree in aerospace engineering from MIT, who has specialized in building decarbonization. He is also a committed climate change advocate. Yannick, welcome to Engineering the Future.
Thank you. Thank you for having me on.
Okay, let's jump right into it. Yannick, can you tell us a bit about your engineering journey and how you went from aerospace to climate activism?
I've had a pretty diverse career. I started out in aerospace engineering, but I moved to nuclear engineering after a few years, and I was a nuclear engineer for 9 years. But where I became really interested in climate change was in December 2009 with the failure of the Copenhagen summit. Back then, I was just curious about this discrepancy I saw between the dramatic alarm that that scientists were raising and the apparent apathy from politicians. And this seemed to be too important of an issue for me to simply sit on the fence. So I wanted to get up to the bottom of this. I wanted to figure out who was right. And what I found was absolutely terrifying, worse than what you normally hear in even from the scientists, who tend to be very reserved. And so once I knew, then I couldn't stand idle. I had to be a part of it. I had to change everything in my life to try to have as much of an impact on pushing back climate change as I could.
What were some of the first things that you were able to change in your day-to-day vocation?
Well, I started looking at things like reducing car travel and air travel. Later on, bought an electric car. I installed a geo-exchange heat pump at my parents' house, and that was the start of a career change for me to go into the building sector to try to reduce emissions there, to have a more direct impact.
And what percentage of the built space is energy intensive? Like, what are we talking about when we talk about heating buildings, the energy required in these spaces?
Well, so I don't think of it much in terms of the amount of energy. I don't see energy consumption as the issue. It's really the amount of pollution put out that's the issue. Sometimes I like to say it's not an energy problem, it's an entropy problem. And in Canada, the amount of emissions that come out of our buildings can be quite substantial because we have quite a cold climate. I was looking up some figures before the show, and nationally, it's 1.9 tons of carbon dioxide per capita is the average across the nation.
How crucial is the integration of environmentally friendly heating and cooling solutions in the broader context in the fight against climate change? And what role can engineers play in driving this transition?
So in terms of how important these heating and cooling is to addressing climate change, that depends on geography. If you look at the global level, it's not that important because most of the world does not have a cold climate like Canada does, right? So globally, the heating and cooling of buildings only accounts for about 6% of global emissions. But if you drill down to a place like the city of Toronto, where we don't have that much industry, the transit commutes are relatively short, then and there's no oil and gas extraction within the city, it's all buildings, then building heating and cooling accounts for 52% of the city's carbon emissions.
Oh, that's very interesting. So it definitely plays a role of where you're located, basically, and how effective these practices will be in reducing the overall energy consumption of your space or your area.
Well, it changes what share of your emissions that this is important for. It also matters like how clean the electricity is in your area.
Right. Okay, so in terms of residential applications, how can engineers listening out there leverage environmentally friendly heating and cooling technologies, not only to contribute to sustainability, but to achieve cost savings in their own homes?
Well, if you're looking to improve or reduce the carbon emissions from heating and cooling in your homes, some of the first things to look at would be the insulation and whether the insulation can be upgraded in the walls or in the attic, or perhaps in the basement as well, and whether it might be it might be worthwhile to replace the windows or to apply caulking, weather stripping to reduce leakage through the building envelope. But all this is going to depend on how old your building is. You talked about improving sustainability while reducing costs at the same time. Well, there are often opportunities to do that, but that's usually either because the technology has changed since a home was built, for example, with the development of ECM fans, or because resource costs have changed, for example, due to the rising carbon tax. So as that landscape changes, then it becomes worthwhile in general to apply the newer technologies that are less carbon intensive.
Is there help available for homeowners that want to go down this path?
There is. I don't have the latest incentives for homeowners off the top of my head. I believe there are federal government incentives available right now for the installation of heat pumps, but I'm afraid I'm not up to date on the latest incentives.
Okay, but there are incentives out there, and they're rolling from federal and provincial levels. Do you feel that the government could be doing more to incentivize this transition right now?
There's always more that can be done. Certainly when it comes to climate change, we are far away from the goals that have been set by the national government and by international bodies like through the United Nations. But in general, trying to solve this problem through subsidies can be, it's not the most economically efficient way to do it because of the free ridership problem. You're going to wind up giving out government money to people who would be doing those upgrades anyway because they're already financially worthwhile because of natural economic conditions. And it also relies on the government to be all-knowing, to be able to prescribe exactly what technologies they're going to give incentives to in order to know what is the best solution for each home. For example, one of the problems that you see in the transportation world, is if you give subsidies for electric cars, well, then the cyclists come wondering, well, where's our subsidy? I guess it comes in the form of bike lanes, but it's balancing the subsidies is difficult. So a better economic way to approach this problem is by is by taxing the things that are bad, by applying a carbon tax and letting the free market decide what are the best solutions to avoid the carbon tax and avoid carbon emissions.
Interesting. That's a new way of thinking about it. When considering retrofitting commercial buildings, how do these technologies present both a carbon reduction advantage and a financial benefit to the client? And what challenges might engineers face in implementing these solutions on a larger scale?
With commercial buildings, as with residential buildings, those opportunities for simultaneously reducing carbon while improving costs depends on the age of your building and what changes have occurred in the technology and available technology and in the resource costs. If there was an easy miracle solution available, the original builder would already have used it. Nobody intentionally builds a less sustainable building that costs more. In terms of the challenges that you get with scale, there are going to be challenges in terms of of manufacturing output and labor availability. But seen another way, that means that there's plenty of potential for job creation in the manufacturing and trade sector, and Ontario could really use that.
I see. Moving right along, let's take a deep dive and talk about technologies in this space. Heat pumps are a key player in the energy-efficient HVAC landscape. Can you describe what a heat pump is and what design considerations should engineers keep in mind when incorporating them into residential and commercial projects?
Sure. Heat pumps are a very valuable technology to help with decarbonization, because that is an efficient means to replace fossil fuel combustion, usually natural gas boilers or furnaces, with electric heating without having your operational costs go through the roof as they would with pure electric heating. So heat pumps are machines that move heat from a colder space to a warmer one against the natural flow of heat. An air conditioner is a type of heat pump, and so is a refrigerator. They're usually used to cool spaces, as in air conditioning, but they can also be used to heat spaces just by flipping the outdoor heat exchanger with the indoor one. And you don't need to physically move the heat exchangers. You can do the flip in the plumbing simply by adding a reversing valve to the refrigerant system.
I've heard that some major brands aren't even making air conditioners anymore. They're just making heat pumps that could be used as air conditioners.
Well, I don't know what brands those would be. I know several brands that offer both, but the only difference between the two models is whether the units have that reversing valve or not. There are some other considerations that have to be taken into account when designing a heat pump to do both. There may be a need for a larger accumulator volume of refrigerant, and generally you're going to need to go to larger units when you go to heat pumps for the Canadian climate, because you have a higher heating demand in Canada than you do cooling demand.
We hope you're enjoying this episode so far. At OSPI, we're here for you, making sure government, media, and the public are listening to the voice of engineers. You can learn more at ospi.on.ca.
So what is the limits of an air source heat pump today? I know that the technology is continuously getting better and better all the time, but can a Canadian use it as their primary source of heat in the winter?
If you're talking about a ground source heat pump, then yes, certainly that your ground source heat pump can operate all winter long, because the temperature in the ground is going to be very stable. The ground forms a very large thermal reservoir. It's essentially thermal storage right there that can store heat, accumulate heat in the summer that you can then extract out of the ground for use in the winter. If you want to heat your home with an air source heat pump, that's a little more challenging. Because in practice, most of the air source heat pumps available on the market today only work down to about -10, -15 degrees Celsius. There are some that you can sort of push down to -20 Celsius, but they're certainly not very efficient at those temperatures. And they become close to being just a straight electrical heating. But we don't actually have that many hours of the year in most of the populated areas of Canada that are really that cold. So if you have an air source heat pump taking up the bulk of your heating needs through the moderate temperature regions, and then you have to supplement that with a little bit of electric heat in the coldest portions of the winter, then that can still work out to an economically attractive package in light of the rising carbon tax or in light of the costs of the damages of climate change.
So economic savings in the future for that person that installs the state-of-the-art heat pump tomorrow.
Well, economic savings relative to ignoring what appears to be the overall policy directions that the world is going in, which is to apply costs to carbon to discourage people from using fossil fuels. But overall, we are talking about a more expensive future to address this problem of climate change.
Absolutely. Well, that sounds like a very promising, exciting technology. Can you tell me about some other concepts? Let's talk about thermal storage. I've heard that this is a concept that's gaining a lot of attention for its impact on energy efficiency. What is thermal storage?
Yeah, well, I already described a simple form of thermal storage with the ground source heat pumps. So ground source heat pump is a heat pump that takes its heat from the ground by having a buried heat exchanger. And in that kind of a system, the ground will accumulate heat from incoming sunlight during the summer, and then the heat pump will extract that heat out of the ground and put it in your house during the winter. So that gives you essentially seasonal storage of heat. There's an even simpler way to do thermal storage, which is simply by having a lot of thermal mass in your building. If you have, for example, if you have heavy concrete walls, unfortunately, the manufacture of concrete is very carbon intensive, so that's not really a good decarbonization solution overall, but it is a thermal energy solution. But the newer thermal energy storage solution that show more promises in the future is to use liquid storage or ice storage or some other phase change material to actively store heat at times when energy is easily available, and then extract that heat back out when heat is needed. And the reason why this is valuable is because it can help us manage the increasing rigidity of our electric grid that is naturally going to occur as we move away from fossil fuels. Nuclear, solar, and wind power don't see any significant fuel savings or personnel savings when they're dispatched down. Practically all of their costs are in the depreciation of equipment. And that doesn't slow down when we use them at part load. This is different from our past when we were running on coal and gas generators, which we were happy to ramp up and down to match demand because those traditional generators were very cheap when they're not running. But now we're moving towards generating sources that cost the same whether they're running or not, and therefore it is worthwhile to maximize the amount of electricity that we can draw from them when that power is available, and then time shift it to when it is useful.
Can you explain that process? I've heard that the new development called The Well downtown Toronto is a prime example of this. It has an Olympic-sized pool reservoir of water in their basement, and it's supposed to be able to regulate how much energy is required to heat the building in the winter and cool the building in the summer. How is that possible?
Yeah, that's right. So the Well, it's definitely going to help store cold water in the summertime. There was a proposal to help it store heat in the wintertime as well. I'm not sure if they actually followed through on those plans or whether they deferred them to future years. But that certainly was a real proposal that was looked at closely. But the idea there, certainly in either case, is to store energy, either in the form of cold water or hot water, at times when electricity is cheap, usually at night or on the weekends. Because there is low demand for electricity at those times, and more because of the importance of wind power, because there's often a lot more wind power available at night. So use that energy when it's available, when the price of electricity is cheap because of high availability and low demand, and use that to generate cold water or hot water and store it in that big tank, that big underground tank, and then pull out that cold water or hot water at other times in the day when electricity is expensive and you'd rather use the stored thermal energy rather than generate fresh thermal energy with electricity.
Fascinating. So we've talked about thermal storage, we've talked about heat pumps. There's basically an alphabet soup of acronyms out there with respect to sustainable building science. Can you break some more of these ideas down for us?
Sure. So the acronyms that usually go together are VAV, DCV, ERV, and HRC. And those are technologies that work on your ventilation system, essentially. Variable air volume is a system that ramps up and down your fan power, your recirculation airspeed or air volume rather, depending on demand. So if you have a lot of cooling needs, your fan will ramp up. If you have low cooling needs, it'll ramp down. It's often thought. A lot of people out there think that VAV is installed for zoning because older buildings are often broken up into zones at the same time as you install VAV. But you can actually do zoning without VAV or VAV without zoning. So the real thing it does is it allows your fan to ramp up and down instead of running at full power all the time. Demand control ventilation changes the amount of fresh air that you take into the building based on the actual occupant load. So that's where you have carbon dioxide sensors, or in some cases, you'd be, in a garage or something, you might be looking at carbon monoxide sensors. But in something like an office building where most of the major contaminant that you'd be looking for would be carbon dioxide. It would be carbon dioxide sensors. The carbon dioxide sensors would control how much fresh air you're taking into the building, and being able to reduce that down in times of low occupancy means that you don't need to condition that fresh air coming in. You don't need to heat it or cool it up to the building temperatures, and that saves you energy.
So the amount of carbon dioxide dictates how busy the building is, how many people are occupying the building at that given moment or day.
Well, it's a symptom of how many people are in the buildings and how hard and how fast their metabolism is. Because we breathe out carbon dioxide, and the more we're working out, the more we're sweating, the more we're going to be breathing out carbon dioxide as well, because the metabolism is higher. And those are indications that the that fresh air needs to be brought into the building. Old air needs to be circulated out.
Fascinating. This is a great conversation. I'm sure our listeners are learning a lot about their HVAC systems if they're not in that space.
Do you want to hear about the other two acronyms, ERVs and HICs? Or?
Absolutely. Go right ahead.
So energy recovery ventilators, they're in many cases an alternative to DCV because what they do is they extract the heat or cool from your exhaust air and use it to preheat or pre-cool your incoming fresh air. So those are your heat wheels or energy wheels, or in a house, modern well-sealed houses, you now see them as these boxes that have to be cleaned every few months. There's this diagonal flow of air. The outgoing air is interlaced with the incoming air to have an exchange of heat. But you can never really preheat the air all the way to from outdoor air from outdoor temperature to indoor temperature with an energy recovery ventilator. So if you want to be more aggressive about recovering the energy in your exhaust, well, then the next step is to go with HRCs, heat recovery chillers. And that's a technology that the company I work for, Ecosystem Energy, actually specializes in. It's particularly useful in larger commercial buildings where a lot of the heat loss nowadays is from that exhaust air because a larger commercial building is going to have relatively low surface area relative to the floor space. The ratio is quite high just because of the volume, the scale. And the ceiling of buildings are becoming much better sealed than they were. So now we're losing very little heat through the envelope, and a major source of heat loss is through that exhaust air. And so that becomes a valuable source of energy to take buildings to the next level.
Wow. So you just broke down the state of the art in the HVAC space. Looking ahead now, what emerging technologies and innovations are on the horizon in the environmentally friendly heating and cooling sector?
Well, in this sector, innovation is largely driven by necessity. So as the carbon tax rises or other policies are put into play to encourage decarbonization, we're seeing more development of a broader variety of heat pumps that are more efficient, can achieve higher temperature lifts. But one of the biggest areas of innovation right now is in the refrigerants themselves and the actual chemistry of them. And one of the things that's driving that is, again, regulation. Just as we have phased out the refrigerants with a high ozone depleting potential, which were causing the ozone hole in our atmosphere, governments are now working to phase out refrigerants with a high global warming potential. And that shift is much more, well, I don't know. It is proving to be more difficult than the last one. I'm not a chemist, but that's certainly the perception I have from the outside. It means just as we moved from chlorofluorocarbons to hydrofluorocarbons, now we're talking about moving to hydrofluoroolefins or possibly back to natural refrigerants. One of the big challenges that we're having in this transition is that a lot of these newer refrigerants that have low global warming potential, they can't bring the flammability down as low as what we've been used to. They're slightly more flammable than the refrigerants we've been used to. So the industry is responding to that by advocating for an acceptance of slightly flammable refrigerants. Slightly flammable refrigerants have long been in common use in many other parts of the world, including Europe. But Canada might be a different situation because we do have a lot more wood construction in this country, because we've historically had a lot more availability of wood. And so we may have higher flammability risks. And so there's some complex discussions going on around that.
Excellent. So would you say that the building code and regulation has a large role to play in whether or not we are successful in this climate transition?
Oh, absolutely. One of the ways that this is driven is, that the transition is driven is through these purely economic approaches like the rising carbon tax. But there's certainly value in many cases through to solve this problem through regulation. in part because oftentimes a lot of builders will have a fairly short time horizon that they think of if they're not constrained by regulation, because to a lot of builders, what they want to do is build these buildings fast and sell them, offload them, and then the energy costs, the carbon costs become the owner's problem. So there's a split incentive problem there that can be addressed by improvements to the building code. It's just valuable to be standardizing the way that we build buildings anyway, in order to overall improve the efficiency of our manufacturing and construction industry. If we can all build them roughly the same way, using roughly the same approaches and technologies. And one of the things that I'd like seen in Ontario is an update to the building code that could bring us up to a more recent version of ASHRAE 90.1. In Ontario, the Ontario Building Code requires compliance to the 2010 edition of 90.1, which is getting kind of old now. This standard gets revised every 2 or 3 years, I think. And I think it's time to bring the building code up to date to call for a more recent version of ASHRAE 90.1.
We've learned so much about building science and HVAC today. I'm sure that our listeners will be walking away with a wealth of knowledge from this conversation. Do you have any final thoughts that you would like to leave our listeners with?
Well, so in most of my answers on what is the right engineering solution to these problems, I try to give impartial advice that will benefit the client based on their needs. But as a human being, as a citizen, I think we should all be putting a lot more emphasis on decarbonization than simply what provides the best personal economic outcome, because we have some big challenges ahead of us that are going to impose eternal costs on future generations. And ethically, as a professional engineer, I don't have any grounds to take that into account in my engineering advice. But as a human, it seems unethical to be imposing those eternal costs on today's on kids that aren't even born yet.
Well, Yannick, thank you so much for sharing your expertise with us today and shedding some light on the cutting-edge innovations that are helping to tackle climate change right here where we live. And as always, thank you to our audience. If you haven't already, please be sure to subscribe and leave a comment or a review. I'm your host, Jerome James. You've been listening to Engineering the Future, and we'll see you next time.
From all of us at OSPE, the Ontario Society of Professional Engineers, thanks for listening. Please be sure to subscribe so you don't miss an episode.